Assalamualaikum warahmatullahi wabarakatuh, and hi there. In this video, we will start with a new chapter, which is chapter 5 in the Statistics for Engineers textbook, which focuses on specific chi-square test. What does this chapter cover? Let's look at the details in the next slide. The detailed coverage of this chapter relates to this chapter learning objectives. At the end of learning this chapter, you should be able to perform a specific chi-square test correctly on these following three topics: goodness of fit test, independence test, and homogeneity test. Next, you should also be able to make a correct decision and write a practical conclusion on these three chi-square tests accordingly. Let's look at goodness of fit test first, which is explained in Statistics for Engineers textbook pages 109 until 116. Recall in chapter 1 when we learned about special, discrete, and continuous distributions such as binomial, Poisson, and normal distributions. In this chapter 1, we just made an assumption that a particular random variable follows a particular distribution. In this chapter 5, however, on the goodness of fit test, we will test if the random variable representing a particular set of data does follow a particular distribution or not. In other words, we want to test how good a particular statistical model or distribution fit the sample data. Thus, we have the name goodness of fit test. There are many types of goodness of fit tests, but in this course, we only focus on a chi-square goodness of fit test. We will see later that the test statistic used in this goodness of fit test is a chi-square test statistic, which summarizes the discrepancy between observed values and the values expected under the model or distribution in question. The narrower the discrepancy between the observed and the expected values, we would expect the closer or better fit the distribution is to the data. The hypothesis test procedure for goodness of fit test follows the general hypothesis test procedure that you have learned in chapter 4, where the null and alternative hypothesis H0 and H1 have to be stated clearly. You need to also state the decision rule, identify and calculate the test statistic, and finally make a decision and conclusion related to whether or not the model or distribution under H0 fit the sample data or whether the sample data follow the assumed distribution or not. For goodness of fit test, how do you write the hypothesis statements? In this topic, the null hypothesis should be written like this, where under H0, the sample data are assumed to follow a particular statistical model or distribution, where the distribution can be characterized by the parameter theta. Here, the theta value can be either known or unknown. On the other hand, under the alternative hypothesis H1, we assume that the data do not follow the distribution assumed under H0. The rejection or decision rule is only one, that is, reject H0 if the chosen test statistic chi-square test is greater than the critical value chi-square alpha nu. Notice that we only use a greater than sign here, and the critical value is at the whole alpha, not alpha over 2, which means we only have one critical region on the right, which is defined by the set of chi-square values greater than chi-square alpha nu. The chi-square test statistic is defined as follows. This formula is available in the statistical table booklet, page 3. Finally, the decision and conclusion must be written clearly to complete the hypothesis test procedure. Now, what are these values? The degrees of freedom nu, the notations K, OI, and EI. Let's look at the following slide for further explanation. If you look at the rejection or decision rule again, reject H0 if chi-square test is greater than chi-square alpha nu. We know alpha is the level of significance. What about the degrees of freedom nu? For a goodness of fit test, nu is k minus p minus 1, where k, which can also be seen in the chi-square test statistic formula denoted here, is the number of classes such that the expected value for the ith class EI is at least 5 for all I from 1 to k. Next, the notation P, on the other hand, is the number of distribution parameters that need to be estimated so that under the null hypothesis, the probability Pi, which is the probability that the random variable x takes a particular value xi, can be calculated. The notation OI refers to the ith class observed value from the sample data and usually is given in a question, whereas the notation EI, which occurs in the condition for k and in the numerator and denominator of chi-square test formula, is the ith class expected value defined as n times Pi, where Pi, as mentioned before, is defined under H0. What is n here? The notation n is the total frequency of the sample data, which should be exactly the same as the sum of observed and expected values. Notice that the chi-square test statistic is the sum of the difference between the observed and expected values squared divided by the expected value over all classes I from 1 to k. In other words, the test statistic measures the discrepancies between the observed and expected values. If the discrepancies are small for all ith classes, you can expect that the assumed distribution under H0 may be expected to fit the data well. We look first at the fed dice example on page 110 in the Statistics for Engineers textbook. Here, a common dice which has 6 faces is tossed 300 times and the results are tabulated as follows. The table shows how frequent the values on the dice have appeared. From this experiment, we can see that number 1 appeared 45 times, number 2 52 times, and so on. The frequencies are actually the observed values OI, which represent the sample data. The sample size is 300 in this example, which is the total frequencies, and this is exactly the sum of observed values OI. We will check and make sure later that this is also the same as the sum of the expected values EI. Based on the sample data, we want to test whether the dice is a fair dice or not. What does it mean when we have a fair dice? It means that the values on the dice is expected or likely to occur with the same number of times, right? Concisely, the probability that each value can occur is expected to be the same or uniform for all 6 values, that is 1 over 6. Therefore, to answer whether the dice is fair or not is actually to investigate if the probability distribution is uniform or not. In summary, we want to test if the sample data follow a uniform probability distribution. So we have a goodness of fit test in this example. Let's look at the next slide on how we should proceed with this goodness of fit test example. Proceed with the fair dice example. Under H0, the dice is fair, which implies that under the null hypothesis, the values on the dice when the dice is tossed, denoted by the random variable x, follow a uniform probability distribution with a parameter 1 over 6. The value 1 over 6, denoted by pi, is the probability that x equal to a particular value xi, for xi equal to 1, 2, until 6. On the other hand, under H1, a dice is not fair, that is, the distribution for x is not uniform. Alternatively, you can also write the hypothesis statements like this, where under H0, the probabilities px equal to 1, px equal to 2, and so on are all the same, that is 1 over 6, whereas under H1, any of the probabilities could be different from 1 over 6. Since we know the probability for each value of x, that is, we know pi under H0, we can then use this value pi to define and calculate the expected value ei for each ith class by multiplying the sample size n, or the total frequencies, by pi or pxi for all I equal to 1, 2, and so on until 6. After which we can calculate the chi-square test statistic. Notice that in this example, the number of parameters to be estimated, denoted by p in the degrees of freedom formula, is 0. Why is that so? Because we do not have to estimate any parameter in the distribution to work out the values of pi, as we already knew the pi values based on the distribution characteristic. We are still looking at the fair dice example. Now we can list down the observed values OI and the corresponding expected values EI for every ith class as follows. Since we know the value of pi, which is 1 over 6, then we can work out the values of EI by multiplying 300 with 1 over 6, giving us 50 for all classes. Before we go into the last column, we need to check two conditions. First, is every expected value EI at least 5? In this example, yes. You can see that all classes have EI equal to 50. If yes, then we can identify how many classes we actually have in this example. Here we have 6 classes, that is, the number of classes k is equal to 6. The second condition we should check before going into the last column: are the sums of observed and expected values the same? We can see that the sum of OI and EI are 300. Yes, they are the same. So if they are the same, only then we can proceed to calculating the values in the last column, which is the squared difference between OI and EI divided by EI. The sum of the last column values is the chi-square test statistic value that we should use in this goodness of fit test, which in this example is 6.2. Let's look at the complete solution in the following slide. After calculating the test statistic value, do not forget that we must write the division rule, which is to reject H0 if the chi-square test statistic is greater than a right-sided critical value, which is chi-square alpha nu. We know alpha is 0.05 in this example, whereas the degrees of freedom nu is k minus p minus 1 given by 6 minus 0 minus 1, which is 5. The way we found k and p has already been explained in the previous slide. Therefore, the decision rule is to reject H0 if chi-square test statistic is greater than the critical value chi-square 0.055 given by 11.0705 from the statistical table booklet, page 36. Now, by comparing the test statistic value with the critical value, we can see clearly that the chi-square test statistic value, which is 6.2, is smaller than 11.0705. Therefore, we can decide not to reject H0 and conclude that at the level of significance alpha equal to 0.05, the dice is a fair dice. Or we can alternatively say that we do not have evidence at 5% level of significance that the dice is not a fair dice. There are 3 good examples in the statistics for engineers textbook that you can learn and follow closely for a good practice and revision. The first example is example 5.1 on pages 112 and 113. In this example, the probability Pi is given directly, where Pi denotes the probability or proportion of road accidents occurring in the country according to 4 categories. In such a case, we know the Pi values. The number of parameters to be estimated, which is denoted by P, is then 0, which leads to the degrees of freedom nu equal to k minus 1. Again, why is P 0? Because we know the Pi values. We do not have to estimate any parameter from the distribution, since we know the Pi values which are given directly in this question. So we can identify the value of nu, which is simply k minus 1. You can also observe from the example on how to formulate the null and alternative hypothesis and check if EI is at least 5 for every ith class. EI, as you know, is the product of the sample size n, which is the total observed values OI, and the given Pi. You may also learn how to calculate the chi-square test statistic using the same approach as we did in the fair dice example. And finally, you can learn how to make a decision and conclusion on the claim that the proportions of road accidents follow the stated proportions or distribution under H0. In examples 5.2 and 5.3 in pages 113 until 115 from the statistics for engineers textbook, the distributions are known and all distribution parameters are given under H0. Again, in these 2 examples, we have P, which is the number of distribution parameters that need to be estimated, is 0. And hence, the degrees of freedom nu equal to the number of classes k minus 1. For example, in example 5.2, under H0, we have a random variable x, which is the number of students who played truancy follows a discrete Poisson distribution with mean 3 per day. So, the parameter lambda is known to be 3, and we do not have to estimate this parameter value since it is given. Similarly, in example 5.3 under H0, we assume that the variable x, which represents the adult IQ scores, is assumed to follow a normal distribution with mean 110 and variance 10 squared. Again, both parameters mu and sigma squared are known. Therefore, the number of parameters to be estimated in this example is also 0. Please note that in these two examples, the PI values are not given directly. So, before you can calculate the expected values EI and hence the chi-square test statistic value, you must first calculate the values of PI based on the distribution assumed under H0. Therefore, please recall the skills you have learned in Chapter 1 when dealing with Poisson and normal random variables. Next, from these two examples, you can observe how the null and alternative hypotheses H0 and H1 are stated. You can also check the EI is at least 5 for all I classes and learn how the chi-square test statistic is calculated in each example before finally learn how to make a correct decision and conclusion on whether the variables follow the distribution in question. For more examples on goodness of fit test, please watch the next video. Until then, thank you very much. Assalamualaikum warahmatullah and see you very soon.